So the next type of collision that we're going to talk about is inelastic collisions. As you can guess, inelastic collisions are kind of different from elastics. So in this case, when one car hits the other, they stick together. Okay, so as you can see in the video, one car is moving and the other one hits it, but they stick together and move together. Right? I will analyze and interpret data from inelastic collisions to explore the conservation of momentum using mathematical representations and experimental investigations to understand how objects interact and behave after a collision. Okay, so as I said, an inelastic collision happens when two or more objects collide and then they stick together. Okay. Kind of like two vehicles colliding, right? Sometimes if somebody rear ends you, they kind of stick to your car, and you have to get somebody to get them apart. So the before is you have, a mass. It doesn't matter what size mass. It could be small. It could be large. Um, and it has a velocity, so therefore it has momentum. And then you have a second mass. Could be big, could be large, or could be big, could be small, could be the same size as the other one. I also having a velocity. Okay. And then one is going to hit the other or vice versa. And then after the two of them stick together, right? So now I have um, three like kilograms. Okay. And then it has its own velocity when it goes, right? So the equation we're going to use is the mass of the first object times the beginning velocity of the first object plus the mass of the second object times the velocity of the beginning velocity of the second object. That's going to equal mass 1 plus mass 2. So the two masses combine to become one mass, right? And then in the end, we have just the one velocity. During an inelastic collision, the energy is not conserved. So if you remember from elastic collision, the energy is conserved. In an inelastic collision, the energy is not conserved. Okay? So inelastic collisions in 1D, right? So in other words, the objects are moving in the same plane of motion before and after. Okay. So example, you have two balls that are heading straight on at each other and then they stick together and still move in that plane, right? So kind of like a football player, you got two of them, they kind of stayed in the same plane, they stuck together. So a perfectly inelastic collision happens when the maximum amount of kinetic energy is lost. So, for example, you have two football players. They collide, stick together, and stop. Okay? So, if they stop, that means that the total amount of energy, right? That's the largest amount of energy that they could have had. Okay. So, here's a sample problem. We have a 1,850 kilogram luxury sedan, and it stopped at a traffic light. And it's struck from the rear by a compact car with a mass of 975 kilograms, right? So the compact car is almost half of the size of the luxury sedan, okay? The two cars become entangled. That means that they stick together as a result of the collision. If the compact car was moving at a velocity of 22 meters per second before the collision, what is the velocity of the entangled mass after the collision? Okay, so let's kind of get in our mind right? You've got this luxury sedan and it's stopped at a traffic light, and then you have a compact car, and the compact car is moving 22 meters per second. That's like 50 miles per hour. Okay. So 22 seems like it's not that big, but this at 22 meters per second is like 50 miles an hour. Okay. So that car is going to rear end the other car, right? And afterwards, those two are going to get stuck together, right? And they're going to move with some sort of velocity. Okay. All right. So identifying our givens, mass 1, I'm going to call the compact car. Mass 2, I'm going to call that the luxury sedan. And then U1 is 22 meters per second. U2 is 0 meters per second. And then afterwards, it's just the two cars that are attached to each other. Okay. All right. So again, step 2, write the correct equation for solving the problem. Okay. Don't skip this step. It's really important, because if you skip this step, you could accidentally put the numbers in for a different equation. Okay. So at least here you have something to follow. Okay. So M1U1 plus M2U2 equals M1 plus M2 all times V. Okay. So then I'm going to fill in my knowns. My M1 is 975, my U1 is 22 meters per second, and the sedan is 1850, and he's moving at 0. They crash together and end up with 975 plus 1850 going at, I don't know what meters per second. Okay. So 4th step, fill in your knowns and solve. Okay. So I'm going to fill in what I had. So my 975 kilograms times my 22 meters per second, right? I'm going to multiply those. I get 21,450 kilogram per second, or kilogram meters per second. 1850 times 0, of course, is 0. On the other side, I get 975 plus 1850 kilograms, giving me 2,825 kilograms times the ending velocity. Okay. In this particular example, it's pretty straightforward. We want to get V by itself, so we're going to divide by the 2,825 on both sides. We end up with V is 7.59 meters per second. Okay. Does that make sense? Well, let's see. The compact car was going 50 meters per second. I called the luxury sedan a van. And the van was going 0. Okay. In the end, the two of them stuck together, and they're going approximately 17 meters per hour. Miles per hour. So we went from 50 miles per hour down to 17 miles per hour. Does that make sense? Yes. The ending velocity is considerably less than the beginning velocity, right? And because the compact car and the luxury car, they're of a mass when they're together, that is a good size, but it's that 50 miles per hour gives it enough momentum, right, that it moves the van, right? So it moves the van 7.59 meters per second, which is about 17 miles per hour, right? So one hits the other, pushes the cars kind of out into the center of the intersection. Okay, so yes, it makes sense. Okay, inelastic collisions in 2D are a bit simpler than the ones in than elastic ones, right? So you'll either have one of the two um, having an angle, like moving at an angle before the collision, or you'll have two objects moving, one in the x plane, one in the y plane, that collide together, and then the um, the two in the end, after they're combined together, move off at an angle. Okay, so in my picture here, I have two balls that are moving, one in the x, one in the y, and then after they collide, they become um, three times the mass, and then move away at an angle. Okay, just like in elastic collisions, you still have to think about the x and the y components of the momentum, and they are conserved and they are treated independently of each other. Okay, therefore, a momentum conservation equation would be calculated in both the x and the y dimensions, and then be combined to find the magnitude and direction of each object, right? So you're going to work to find the velocity or whatever it is you're trying to find in the x direction. You're going to work to try and find the velocity in the y direction, and then you're going to square those two, add them together, and then take the square root to get the ending velocity. Okay? So to sum it up, inelastic collisions happen when two or more objects collide, then stick together, and then change motion. Okay? Usually it's they collide and either keep moving in one direction, or change directions and move the other direction. Okay. Inelastic collisions in 2D, the before is angled, or the objects colliding move at an angle to its original direction. Okay. The equation is mass 1 times beginning velocity 1 plus mass 2 times the beginning velocity of 2. If we had more than that, more than just 2, you would add another plus in there and put another m and another u, equals the total mass, right? Take all the masses and add them together, and then there's just one velocity at the end.